Okay, so the second part of Unit 9's objectives is transforming the other four trig functions. 9.1 was all about sine and cosine. 9.2 is all about tangent, cotangent, secant, and cosecant. Today we're going to focus on tangent and cotangent. So this is a two-part video, so it won't be really long. And today also we are just going to focus on stretching and compressing without any shifts. So the essential question is this: how do I use critical points, the amplitude, the period, and a few cycles to sketch graphs of tangent, cotangent, and for tomorrow, secant and cosecant? Okay? And I typically will, either when I'm doing my graphs, have out my unit circle, or I will have my table of exact values handy, or I will quickly sketch out a unit circle so that I can use it. Okay, things to remember. Tangent and cotangent, which is our focus for today, can be decomposed into sine and cosine. True? So what I'm going to do over here in this side is just going to indicate some things that I'm going to do on the unit circle in red. Tangent of x, if I decompose it, is the sine of x over the cosine of x. And cotangent of x, decomposed into sine and cosine, is cosine of x over sine of x. And on my unit circle, I can see those values pretty easily. And I'm going to pause the video for a second and go fill up my water. Okay, so we have a couple of formulas here, or equations of tangent and cotangent. And what we're going to do is give you the formulas that will help you to find amplitude, period, and phase shift, talk about how many critical points there are for graphing, and figure out what one cycle of a cosine or a cotangent or a tangent branch. These are not waves, they're called branches. Okay, amplitude, again, I'm going to continue with my color coding. Amplitude is still the absolute value of A. Period. However, for tangent and cotangent is different, and I'll illustrate that on the unit circle here in just a second. Period is pi divided by the absolute value of B. So you'll see one full branch of the tangent or cotangent function over a period of pi divided by B. And phase shift, because we're not doing these today, I'll just do it in pencil, is still the opposite of C over B. So notice the one change. Yes? The period is cut in half. It's not 2 pi over B, it's pi over B. Okay, y equals tangent of x has, I'm going to switch to green for a second, 5 critical points. Cotangent of x also has 5 critical points. These critical points do include asymptotes. And tangent has one cycle, and I'm going to continue with my green, of negative pi over 2, less than but not equal to bx plus c, less than pi over 2. And what I want to indicate to you is this: these two terms on each end of the cycle are your asymptotes. Okay, so 2 of your 5 critical points are asymptotes. And then one cycle of the cotangent function is 0, is less than bx plus c, is less than pi. So a period of pi, where again, these outside terms are asymptotes. Okay, so before we graph, what I'd like to do is just sketch a unit circle over here so we can look at it. And then you can decide if you'd like to illustrate your notes with the unit circle or if you just want to watch what's happening. Okay, so I'm not going to draw the circle if you're okay with that, but I am just going to go ahead and put in my, my angle changes. So at 0 degrees on the unit circle, I'm at 1, 0, right? Cosine is 1, sine is 0. And then when we graph tangent and cotangent, we usually also graph the pi over 4s, the 45-degree angles. So at pi over 4, on the unit circle, we have a cosine of square root of 2 over 2 and a sine of square root of 2 over 2. At pi over 2, on the unit circle, cosine is 0, sine is 1. At 3 pi over 4, cosine is negative square root of 2 over 2. Sine is the square root of 2 over 2. At pi, cosine is negative 1, sine is 0. 5 pi over 4, negative square root of 2 over 2, negative square root of 2 over 2. At 3 pi over 2, you're at 0, negative 1. And we just have to do one more rotation of 45 degrees. At 7 pi over 4, you are at the square root of 2 over 2, negative square root of 2 over 2. Now, why did I do that? Because on the unit circle, if I decompose tangent into sine over cosine, I'm going to pick up my red pen to indicate what I'm doing here. Typically, when we graph a cycle or 2 cycles of the tangent function, we start at a positive rotation and we'll go from 0 to pi over 4 to pi over 2 to 3 pi over 4 to pi. Okay, so watch what happens when I do my my tangent. 0 divided by 1 is 0. So I'm going to graph 0, 0. Then here I'm going to do the square root of 2 divided by the square root of 2, which is 1. And what I'm indicating here with the arrow is there's my numerator divided by my denominator. I'm just talking about my division. Okay, here I get 1 divided by 0. That is undefined. Asymptote at pi over 2. At 3 pi over 4, I'm doing 2 square root of 2 over 2 divided by negative square root of 2 over 2. That is negative 1. Then I get back here and I do 0 divided by negative 1. That is 0. So you can see going through the full cycle of a tangent, 0, 1, undefined, negative 1, 0, 1, undefined, negative 1, 0. Watch what happens. If I divide that, that's positive 1, truth. If I divide this, it is undefined. If I divide this, it is negative 1. So as I go around the unit circle, you can see from negative pi over 2, one cycle, to pi over 2, I'll do one full branch of the tangent function with an asymptote on each side. Watch. Undefined, negative 1, 0, 1, undefined, negative 1, 0, 1, undefined, negative 1, 0, 1. Around and around I go. So let's draw one cycle. Oh, let me get my pencil, sorry. One cycle to look at. And we can just cut that y-axis, that x-axis in half, because we're going to graph left negative pi over 2, right pi over 2, and we're going to draw asymptotes. I'm going to do my critical points in green here. So asymptotes at negative pi over 2 and pi over 2. And then what you do between your asymptotes for tangent and cotangent is you equally divide out the distance between asymptotes into 3 equal sections and 4 equal distances. So 1, 2, 3, 4. And amplitude is 1 and negative 1. And then I'm going to go back to my green pen here. At negative pi over 4, which is this rotation right here, my tangent is negative 1. At 0, my tangent is 0. At pi over 4, my tangent is 1. And then at pi over 2, I have an asymptote. So this is one branch. Notice I'm not calling it a wave. One branch of the cotangent function. So cotangents don't graph waves. Smooth curves called branches. Okay. Now, I'm going to go to my blue pen, and I'm going to come back over here to my unit circle, and I'm going to indicate my cotangents. So cotangents, cosine over sine. So I'll just do this bottom. I'll just go underneath to do cotangent. So 1 divided by 0 is undefined. 1 divided by 1 is 1. I'm sorry, square root of 2 divided by square root of 2 is 1. 0 divided by 1 is 0. Negative square root of 2 divided by square root of 2 is negative 1. Negative 1 divided by 0 is undefined. Positive 1, 0, negative 1, undefined. So you can see from 0 to pi, you'll go through the full cycle of cotangent from undefined, from asymptote to 1 to 0 to negative 1 back to asymptote. There's one full figure there. So we can start the cycle of our cotangent function at 0 and stretch it out to pi, cut it in half, and then cut it in fourths because you want 4 equal sections. Basically, you're graphing every 45 degrees, you're graphing something with an amplitude of 1 and negative 1, indicating that you're on the unit circle, radius 1. And then I'm going to grab up my green pen again, put your asymptote at 0 for one cycle, and the other one at pi. So here's one branch of your cotangent function. Then at pi over 4, you're at positive 1. At pi over 2, you're at 0. At 3 pi over 4, you're at negative 1. And here is one cycle of your periodic function, y equals cotangent of x, without any shifts or stretches or compressions. Questions about that? Okay, I hope you're seeing how useful the unit circle is, helping you to identify your asymptotes. Okay, we're going to skip secant and cosecant for today. We're going to do example A and example B, and then we'll be done. Okay, so let's take a look at the instructions. It says find the amplitude, period, phase shift, sketch the graph of the equation. So I'm going to start with my A term, y equals 4 tangent x. So my A is 4. That means my circle has a radius 4. My amplitude is the absolute value of 4, which is 4. So instead of stretching up to 1 and down to negative 1, I'm going to have to quadruple that stretch. This is a vertical stretch of 4. My B term is 1, right? It's the number, the coefficient of your x. So the period of the tangent function is pi divided by the absolute value of B. So that's absolute value of 1. So it has a period of pi. Because we have to find our phase shift, let's also indicate our C term. Our C term in this case is 0. Okay, so our phase shift is the opposite of C over B. Negative 0 divided by 1. I don't even know why I wrote negative. Yeah. Because it only takes the distance of pi to do one full branch. You don't have to go 2 pi to get the full picture, okay, or one cycle. All right, so your phase shift is 0. And then your D term in this case is also 0, which means there is no vertical shift. So let's indicate that. One other thing I think is important is to use the cycle. So one cycle of the tangent function starts at negative pi over 2, less than your bx plus c. So that's just your x, less than pi over 2. That gives you your asymptotes. Okay, and so when I go to create this graph over here, I need to have some graph to the left of your x-axis, y-axis, and some graph on the y. And I'd like to see a couple of cycles. And let's make the y-axis pretty long because we do have an amplitude stretch up 4, down -4, and then just maybe cut that value in half and then cut it in half again. And then on your x-axis, -pi/2, and then we'll do the same distance on the other side to pi/2, same distance to pi, and then I think let's just go ahead and go to 3pi/2. That's good. And then let's go ahead and put your pi/4s in between so that we have those 45-degree turns so we can get our amplitudes. And then I'm going to grab my green pen in this case. Okay, so I have my two asymptotes here at -pi/2 and pi/2. And because this graph just duplicates, it's periodic, over another period of pi, there's going to be another asymptote. And then, if you don't mind, I'm going to graph the original function, which is here at -pi/4, 1, 0, and +1, so that I can illustrate the amplitude stretch. So I'm just going to do this in a dashed line. Okay, and what I'll indicate over here is that I did y equals tangent of x in a dashed line, just so that you can see the parent function of the graph. And then I'm going to amplitude shift, or amplitude stretch, vertical stretch. So this point here is going to go up to 4, and this point here is going to stretch down to -4. It's just a vertical stretch, up 1, up 2, up 3, up 4, or down 1, and then quadruple your down. So your graph gets really stretched out vertically. So your branch is really, really long and skinny. And then just duplicate those points in the next cycle. It's periodic, so it'll look the same in the next cycle. And then you could also graph to the left if you want, or graph some more to the right. I'm not doing a very good job of drawing my branch here. My pen is not cooperating. And there you have it, an example of an amplitude stretch. Okay, now we're going to quickly go and do the last problem because we have about 6 minutes left of class. I'm going to clear this out and we'll start again. So we're also going to do example B, where we have y equals cotangent of 2x. So I'm going to start with identifying my A, B, C, and D. A is 1. So that means my amplitude is the absolute value of 1 or 1. So at my 45-degree angles, I'm just going to hit the 1 and the -1. Okay, switching to my blue pen, my B term is 2. And the period of a cotangent function is the absolute, or is pi divided by the absolute value of B. So that would be a period of pi/2. So that has a horizontal compression. So the period just got cut in half. So over half a period, I will get 1 full branch. Your C term in this case is 0. So your phase shift is 0/2, which is 0. Your D term is also 0. So that indicates no vertical shift. And one cycle of your cotangent function starts at 0, less than your bx plus c, so 2x, less than pi. And we're going to use this shift, not this shift, but this period change, to indicate where your asymptotes for one cycle go. So we're going to start at 0, in between, x is between 0 and pi/2. So there's one cycle. And I think that's at least draw 2. Your y-axis doesn't need to be quite as deep. And we don't really have to graph much to the left. So we're going to just put in 0 and pi/2 and pi and 3pi/2 That's good. And then let's put our asymptotes in. So I'm going to grab up my green pen. So for one cycle, 0 to pi over 2. That gives you an indicator of how far apart to put all your asymptotes. So at every distance of a quarter turn on your unit circle, you will have an asymptote. So it looks like I'll get 3 cycles here in my picture. And then what you just need to do, we'll put your pi over 4 in there, and then just cut that distance in half so that you have 4 equal distances between each cycle or each set of asymptotes. And I'll put my amplitude in here, my -1 and 1. And I'll do my critical points in green for one cycle. So I'm going to do one cycle in green, and then I'll switch to my pencil. So cotangent starts out high or starts down low? Starts high, hits the center at 0, finishes low. So there's one cycle of your cotangent function. Now I'm going to just switch to my pen, and I'm going to duplicate that in 2 more cycles. So I'm going to draw 2 more branches of this cotangent function. And at least do me the favor with your tangent and cotangent function. Give me 2 full cycles so I can see the pattern developed. Like you could have a half cycle to the left and a half cycle to the right and a full cycle in the middle, as long as I get 2 full cycles. That's it for today. So tomorrow we'll finish up these notes, and then I'll have you do some practice.